Hi, in this screencast I'm going to walk you through Project 4 and give you some hints along the way. Here's the PDF for the project. You can find a link to this PDF on the assignments page of the course website, and on that page you will also find a link to the zip file for the project, and when you download and extract that zip file on your computer you're going to see a folder such as this containing these items in it. Okay, so as usual, the folder contains the starter files for the problems in the project. It contains a report.txt file that you could use as a template when you write your report. It contains runtests.py that you should use to test whether or not your programs meet the input and output specifications. And it contains the subfolder data that has several uh, 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 test files in it that you should use to test out your solutions thoroughly. Okay. All right, so now let's walk through the project in some detail. So this project is called 8 puzzle, and the goal here is to write a program to solve the 8 puzzle problem using a very famous algorithm called the A star algorithm. Okay. Now this the 8 puzzle problem is played on a 3 by 3 grid containing 8 square blocks in it, okay, which are labeled from 1 through 8, and it also contains a blank square. Now your goal is to rearrange the blocks so that they are all in order. Okay, now you're permitted to slide blocks horizontally or vertically into a blank square, and here is an example of the 8 puzzle problem. So you have your initial puzzle, okay, with the blank square right there, and you want to rearrange things such that you eventually get to this final grid where all the tiles are in order. Okay, so this is our initial board and this is our final board. Okay, and what you see here are a sequence of legal moves from the initial to the goal board. So for example, here the way I got here is by moving this tile to the left, so that's that, and then from here to here what I did was I've moved 2 above, so I have that, and then from here to here what I did was I moved 5 to the left, and then finally I moved the 6 above, and I have my solution, okay, the goal board. Okay, so that's the 8 puzzle problem, and this problem can be nicely generalized to a grid that is size n by n containing n square minus 1 square blocks labeled from 1 through n square minus 1, and has a blank square, and then your goal is to again follow a sequence of legal moves and take the initial configuration of the board to its final configuration where all of the squares are in order. Okay, all of the squares from 1 through n square minus 1 are in order. So that's a generalization of the 8 puzzle problem to an n puzzle problem. Okay, all right. So what we're going to do next is describe a solution to the problem that that uses a general AI methodology known as the A star search algorithm. Okay, so here what we have is a search node. Okay, and for our n puzzle problem here, the search node of the game is going to be a board. All right, and then the number of moves made to reach that particular board, meaning that particular configuration, and also a previous search node. Okay, so so the search node of the game is going to be a board, the number of moves made to reach that particular configuration or that particular board, and a previous search node. Okay, and then what we do is we first insert the initial search node, which is basically the initial configuration, 0 moves and null previous search node into a priority queue and a minimum priority queue. All right, so we insert the initial search node, which comprises of the initial board, 0 moves, and a null for the previous search node, into the priority queue. And then we delete from the priority queue the search node with the minimum priority. Okay, we'll talk about what it means to say that the priority is minimum. Okay, so we delete from the priority queue a search node with the minimum priority, and we insert onto the queue all the neighboring search nodes of that particular node, meaning those search nodes that can be reached in one move from the search node that was dequeued. Alright, and then we repeat this procedure until the search node that was dequeued corresponds to the goal board, meaning the final board where all the tiles are in order. Okay, so this is basically the A star search algorithm. Alright, so now what we need to do next is talk about this notion of priority. Okay, so we're going to talk about two priority functions here, and they're called Hamming priority function and Manhattan priority function. So in the Hamming priority function, it's what we have is that it's basically the number of tiles in the wrong position plus the number of moves made so far to get to the search node. Okay, so the Hamming priority function is a function of a particular board, right? And what it returns is the number of tiles that are in the wrong position plus the number of moves made so far to get to that particular configuration or that particular search node. Okay. Okay. And then the Manhattan priority function is again a function of a search node, and that is simply the sum of the Manhattan distances from the tiles to their goal positions plus the number of moves made so far to get to that particular search node. Okay, now a Manhattan distance is basically the sum of the vertical and horizontal distance from of the tiles from their goal positions. Okay, so let's look at a couple of examples, and this will make it very clear. So let's say this is our initial board. So and let's say that this is also our initial search node, right? So there's no previous search node here. So this is our initial search node. So the number of moves made so far to get here is basically 0, and there is no previous search node. So the question is, what does the Hamming and the Manhattan priority function return for values for this particular search node? So let's talk about the Hamming function first. Okay, so so how many of the tiles here are in the wrong position? We first arrange all the tiles in order, so 1 through 8 in this case, and then we check if each of the tiles is in the right position in the search node. Well, 1 is not in the correct position, right? Because 1 really belongs here. So we we say so we include a 1 for that. And then what about 2? Well, 2 is not in the correct position either, because 2 really belongs there, so we take a 1 for that. And then what about 3? Well, 3 is in the correct position, so there's no penalty there, so that's 0. What about 4? That's in the correct position. What about 5? Well, that's not in the right position because it needs to belong there, whereas it's there, so a 1 for that. And then 6 is not in the right position, and then 7 is in the correct position, whereas 8 is not, so 0 for 7 and 1 for 8. Okay, so the Hamming priority function for this particular search node is going to return the sum of the ones here, which is 5 plus 0, because this is the initial search node. Okay, so there were no moves made to get here, so it's basically 5 plus 0, which is 5. Right. What about the Manhattan priority function? What is that going to return for this particular search node? Well, again, we arrange all the numbers 1 through 8 in order, and then we, for each one, we look at its distance to the goal position. Okay, um, so one is there, but what is its Manhattan distance to where one really belongs in the goal position, which is that one, right? So the way I can get from there to there is just by one move to the left. Okay, so from here to here. So that's why I have a 1 there. What about 2? Well, 2 is right there. It needs to belong there. So how do I get there? Well, the Manhattan distance is basically, go up and left or left and up. So that's a distance of 2. Okay. What about 3? Well, 3 is in the right place, right? So it has a Manhattan distance of 0. What about 4? That's also in the right place. So that has a Manhattan distance of 0. What about 5? Well, 5 is over there, but it needs to belong there, and the way I can get from there to there is either by going to the left and up, which is a distance of 2, or by going up and then left, which is again a distance of 2. So that's what I have there. Okay, and then likewise, the Manhattan distance for 6 is 2, the Manhattan distance for 7 is 0 because it's in the right place, and the Manhattan distance for 8 is 3. Why is that? Well, 8 is currently there, but it needs to belong there, right? Because that's the goal position. So how can I get from there to there? Well, I go down 1, down once more, so that's 2, and right. Okay, so it's basically 3. Or I can go to the right and then come down and down, so that's 3 again. All right, so the Manhattan priority function for this particular search node is going to return the sum of these numbers, which is 10 plus 0 because this was the initial board, and that is 10. All right, so that's how the Manhattan and the Hamming priority functions behave. All right. Next, we need to talk about a couple of very critical optimizations. Okay, now the first one has to do with this annoying aspect of the best first search, which is that the search nodes corresponding to the same board are enqueued on the priority queue many times, and we want to avoid that. So so in order to reduce the unnecessary exploration of useless search nodes, what we do is when we consider the neighbors of a search node, we don't enqueue a neighbor if its board is the same as the board of the previous search node. Okay, so what does that mean? Let's take this example here. So let's say this is our search node, and this is the previous node. So the way we got from here to here is by moving this 2 to the left. Okay, so that's my search node, and that's the previous node. Okay, now what are the neighbors of this particular node? Well, I can move this 2 to the right. Okay, or and when I move this 2 to the right, I'm going to get this particular board, or I can move the 3 below, so I get this particular board, or I can move this 5 above and I get this particular board. Alright, so those are the 3 neighbors for this particular search node. But notice that this particular neighbor is basically the previous node of the search node. So this configuration and this configuration are identical. So there is no point in enqueuing this particular board into the priority queue. All right. So when you enqueue the neighbors, make sure that you don't enqueue a board that is the same as the previous search node. All right. So that is one of the optimizations that we need to implement. What is the second optimization? Well, this has to do with caching. So to avoid recomputing the Manhattan and distance of a board, or alternatively the Hamming priority from scratch all the time, what we do is we just compute it at most once per object and save its value in an instance variable. All right. So when we are building a board, we basically compute these values, the Manhattan distance and the Hamming priority, and we just store it as a in an instance variable. Okay, so we don't like recompute these things unnecessarily. So this is essentially like a caching idea that we need to implement. So that's going to be our second optimization. All right. Now, it turns out that a nice way of looking at the best first search algorithm is as a game tree, and that is what is shown here. And I encourage you guys to read this carefully and make sure you understand, like why we have these things in this figure. Okay. All right. Okay. So the next thing that we need to talk about is an important idea, which is how do you detect if a certain puzzle is solvable or not. So it turns out that not all initial boards can lead to a goal board by a sequence of legal moves, and here's an example that illustrates that. Okay, so these two initial boards are unsolvable. So the question is, how do you detect such situations? Okay. So basically, given a board, you want to be able to tell if you are going to be able to solve that puzzle or not. Meaning, if you're going to be able to take that board through a sequence of legal moves into the goal board. Okay. So the question, so we want to be able to detect that. All right. Now, it's fairly straightforward to figure that out, but to do that we need an idea called inversion. All right. So given a board, an inversion is basically any pair of tiles ij where I is less than j, but I appears after j in the board. When you consider the board in what is called the row major order, meaning row first followed by row 1, row 0 followed by row 1 followed by row 2, and so on and so forth. Okay. So let me repeat, an inversion is basically a pair of tiles I and j where I is less than j, right, but I appears after j in the board. Okay, so that's an inversion, right? So let's take some examples. So let's say this is our board. All right. So here, how many inversions do you have? Well, if you just unfold these numbers in the row major order as such, we see that you have this pair 8 and 7. So so 8 appears after 8 appears before 7 in the board, but it really belongs after 7. Okay, so it should really be 7 and then 8, but in the board it shows up as 8 and 7, so that's an inversion. Okay. So that's that. And let's take another example. Let's take this one. Okay, and if you unfold the numbers, this is what you see. So how many inversions do we have here? Well, you have 6 5, so they are out of order, and then you have 8 5, and then finally you have 8 7. So there are 3 inversions here. Okay, so that's the notion of an inversion. Now it turns out that if you're given a board that has an odd size, meaning if n is odd, then if that board has an odd number of inversions, then there is no solution to that board. Okay, so let me repeat. So if you're given a board that has an odd size, meaning n is odd, and if the number of inversions for that particular board is odd, then you can conclude that the board is unsolvable. Okay, but what about the case where the board has an even size? So in that case, what you need to do is so if n is even, then you need to look at the number of inversions for that board plus the row number of the blank square in that board. All right, so you calculate the sum of the number of inversions plus the row number of the blank square, and if that quantity is even, then you conclude that the given board is unsolvable. Okay, so when n is even, you basically look at the sum of the number of inversions for the board plus the row number of the blank square, and if that quantity is even, then you conclude that the board is unsolvable. Okay, so that's how you figure out if a given board is solvable or not. Okay, so now let's talk about the first problem in the project. So here you're supposed to implement an immutable data type called board in board.java that models a board in the end puzzle problem and has the API that is shown here. Okay, so it has a constructor board that takes a two-dimensional array of integers called tiles as an argument, and it constructs a board from those tiles. All right. Now here, when you implement this constructor, make sure that you make a defensive copy of the array that is given to you, and don't just directly assign this to the instance variable, but make a copy of it. All right. So, okay, so that's that. And then there is this method called tileAt that returns a tile at row I and column j, or 0 if it is blank. Okay, so it's basically supposed to return the tile number. All right. So that's that. And then there's this method size that returns the size of the board, which is simply n. Then this method hamming is supposed to return the number of tiles that are out of place. Okay, so and then Manhattan is supposed to return the sum of the Manhattan distances between the tiles in the board and the goal. Okay, now again here, when you implement these methods, make sure that you implement them in constant time. All right, again, remember the caching idea that we discussed earlier. Okay, and then there is this method isGoal that returns true if the board is the goal board, and false otherwise. There's this method isSolvable that detects whether or not the board is solvable and returns that as a boolean. And then there is this method equals that compares this board versus that and returns true when the two boards are identical and false otherwise. And then since this data type is an iterable data type, then there is this method called neighbors that simply returns the neighbors of this particular board as an iterable object. Okay, so it returns all the neighboring boards as an iterable object. And then finally there is this method toString that returns a string representation of the board. All right. Okay, so as usual, make sure that your implementation meets the performance requirements that are stated here. Now so once you have your implementation done, you can test it by running this command on the terminal. Okay, so this basically runs the test client that is defined in board, and if your implementation is correct, then for this particular puzzle you ought to get this output. Okay, so that's problem 1. Now let's talk about problem 2. So here you're supposed to implement an immutable data type called solver in solver.java with the API that is given here. Right? It has a constructor solver that takes an initial board as an argument. So initial is simply an object of type board, and then what it's supposed to do is find a solution to the initial board if one exists using the A-star algorithm. Okay, so it's in the constructor that you will basically implement the A-star algorithm. All right, and then there is this method moves that returns an integer, which is simply the number of moves to solve the initial board. And then finally there is this method solution that returns a sequence of boards which will in a shortest solution, meaning it's a sequence of boards as an iterable object that will take the initial board to its the goal configuration. All right, so that's so it's essentially solving the end puzzle problem. Okay. In an optimal fashion. Okay, so here again, make sure that you take care of the corner cases that are listed here, and then once you have your program written up, you can test it by running this command java solver and then the input puzzle, and this runs the test client that is defined in solver. And if your implementation is correct, you ought to get exactly this output for this particular puzzle. Okay, so here the optimal solution involves 3 moves, which takes the initial configuration, which is this one, and turns it into the final configuration. Okay, so that's one move. Oh, sorry, this is not 3 moves, it's 5 moves. Okay. Um, okay, so 1, 2, 3, 4, and 5. All right, good. Okay, and then make sure your implementation meets uh, the requirements that are stated here. All right. Okay, so that's problem 2. And now, before I proceed, I want to mention a couple of other clients that are provided to you that you should use to test your solution. Okay, so the first client is called Puzzle Solver or Puzzle Checker, and here you can simply supply it a bunch of puzzles. Okay, so you say Java puzzle checker data star, and then what it's going to do is it's going to run your solver program on each of the puzzles from the data directory. Okay, so when you hit enter, you see this kind of an output. So it'll display the puzzle name. All right, so so in this column you see the files that represent the initial configuration for each of the puzzles, and then it shows you the number of moves that were involved in solving that particular puzzle and the time that it took to solve the puzzle. Okay, so that's a very nice client that you should consider using. And then the other client is quite nice. It's called a puzzle visualizer, or solver visualizer rather. And here again, you run it by saying Java solver visualizer and give it a puzzle. So for example, let's say 05, and we run that. If your implementation of board and solver are correct, then this is what you will see. Okay, so it'll essentially like visually solve the puzzle. All right, so that's that. Let's try it on some other puzzle. Okay. So it's essentially following a sequence of legal moves that would take the initial configuration to the goal configuration. All right. So that's a very nice test client to use. Okay. Now let's go back to the PDF. And then the data directory has several sample input files for you to test your solutions against. Now each file has a very simple format to it. Okay, so it basically has the size of the board, n, followed by an n by n board. Okay. Which is like the initial configuration, and we use 0 to represent the position of the blank square. All right. So for example, if you look at puzzle4.txt from the data directory, you're going to see something like this. So it's a 3 by 3 board, so that's that, and then here's the board. Right, so this is an initial configuration, so that is a blank square. Right? Okay, and then so once you're done with the project, these are the things that you need to turn in: board.java, solver.java, and a report. And as usual, make sure that you use the template that is given to you to write your report. So there it is, and make sure that you fill in all the sections here. All right. And as usual, make sure that you run your programs through runtest.py. Okay, because that's how you test whether or not your solutions meet the input and output specifications. Then make sure you test your programs for style using check style, and then make sure that your reports are not too long, they don't contain spelling mistakes, and they don't contain lines that exceed 80 characters. Okay. All right, so that's all that I had to say for this project. I hope you have fun working on it. It's a really interesting project, and I do hope that you guys learn something from it. All right. Okay. Great. Thanks.